Okay, picking up where we left off last time, when you're calculating Q, you calculate it in the same exact way as you do K, except that you're using initial concentrations or concentrations that have not reached equilibrium, and then you can compare them to the known value of K to see if you're going to shift left, shift right, or no shift. So if your Q equal to K, you're at equilibrium, so there is no shift in the reaction. And then we said reactants to products is a shift to the right. So we usually will just draw that like shift this way, shift right. This would be no shift, and then this one would be shifting towards the left, meaning we would make more reactants. Okay? So let's go through and work one of the problems. So here we have three systems. Predict the direction in which the reaction will shift to reach equilibrium in each of the following cases. So it gave us a K value up here. Here's our K value that we're going to, whoops, forgot to say that I'm writing. So there's K. So we're going to compare all of those to that one. So we're going to calculate Q, products over reactants. I guess we probably should write the equation. It's the synthesis of ammonia, which is N2 plus 3H2 yields 2NH3. All right. So our Q should look like this. For all of them, we're going to have NH3 concentration raised to the second power over the reactants. So we'd have concentration of N2 and then H2 raised to the third.
Doesn't it need to be parentheses?
Nope, these are concentrations. Okay. Yeah, if we were dealing with pressures, they'd be parentheses. But because they're concentrations, it's brackets. So now we just plug all that stuff in there. 1 times 10 to the negative 3 raised to the second power divided by 1 times 10 to the negative 5. And then 2 times 10 to the negative 3 cubed. So when we do that math, we get that Q is equal to 1.25 times 10 to the 7, which is way greater than K. So we would say Q is greater than K.
Are you sure? Isn't that way less than K? You said negative 7?
No, positive 7.
Oh, I totally heard a negative. Yeah.
So Q is way greater than K. So equilibrium, which we would say shift left. Or you could say the reverse reaction would, because this is actually a reversible reaction. I forgot to write that. Okay? And then for the next set, same thing. Now plug all those things in. So we have 2 times 10 to the negative 4th. And that's raised to the second power divided by 1.5. That looks like a 6. All right, that is... So when we do that math, we get Q is equal to 6 times 10 to the negative 2. So Q is equal to K. So no shift. It's already at equilibrium. And then to save time, you're going to plug in the numbers down there. When you do, you get Q is equal to 0.002. And in that case, Q is less than K. So shift right. If you were doing a problem on an FRQ and it asked you to do that, you can't just calculate Q and say you're done. You have to go through the process of saying, because they want to be able to recognize that you understand that the equilibrium shifts are based on you knowing if Q is greater than or less than K. So you must state that. Yes.
Q the reaction quotient.
Q is the reaction quotient.
And the little subscript C like just goes with it.
Yeah, because we're dealing with concentration.
Okay.
So a lot of times we just write Q, but it would be Q of C. If we were doing pressure, it would be QP.
Cool.
But Q is basically identical to K, except that we're not at equilibrium. So we're using initial concentrations.
Okay.
Okay? Any questions on how to do that? Because that brings us to rice tables. Huh? You just get tired of them. They're not hard. Okay, so here we have, whenever we have equilibrium constant, we can solve for concentrations based on something known as a rice table. Some people call them ice tables. Difference is the R is for reaction. Some people leave that out because you have to have the reaction. But it stands for initial, change, and equilibrium. Okay, so what you're going to be doing. Okay, and so the best way to do it is just show you. There's all the instructions, but the best thing is just to show you. Okay. In this first one, we don't actually need a rice table. It's showing you how you could calculate it if you know that. It tells you Kp is 0.133, and it gives you the pressure was found to be 2.71, and it says calculate the equilibrium pressure of the NO2. So when you do Kp is equal to the partial pressure of NO2 squared over P into O4, then you plug in what they gave you. 0.133 is equal to, basically it'll be x squared over 2.71, and then you just solve for x. So x squared would be equal to 0.36043. Take the square root of everything, and so you get x would be equal to the pressure of NO2, which would be 0.600 atmosphere. So that's how you would do that if you have all the information. But oftentimes you don't have the information. They gave you the pressure at equilibrium, and so that's why we're able to do that. Oftentimes they will not give you that at equilibrium. You've got to solve for that. And so that's where the rice table is going to come in on the next problem. Okay? And sometimes you're lucky and you can figure it out mathematically, easy peasy. Sometimes you need the quadratic equation. So if you don't have that formula in your calculator, we need to figure out how to get it in your calculator. Somewhere, huh? Do you have the quad form in your calculator?
No.
Okay.
I mean, I know the quadratic formula. I don't have it in my calculator.
Oh, you should have it in your calculator. It's much easier. Yeah. Somewhere I have a cord, and I can download it from my calculator to other people's calculators. I just got to find the cord and remember how to download the program.
It lets you just like plug
where
in
would
the
it
number.
be at
Yep.
the calculator?
Oh, you have to put it in
It's
there.
like we do the integral thing.
It's in the programs, but it's not usually in there. If you've got a high fancy powered new fangled calculator, it might be in there, but they're old TIs. I have a little cord that you can connect the calculators and I can download it. But I just got to remember how to download it too. I always forget how to download it. Because it's in mine. Speaking of, I'm going to need that. You can also look up the formula of how to program it in, because that's how I had to get it in mine. I had to look up how to program the quadratic equation in my calculator. So, okay, we don't need it on this first one. Okay, so here we have a certain flask, temperature of 1 liter flask. That's going to be important. Contained 2.98 moles of the PLC. Had some PLC5, and said after the system reached equilibrium, it was found to have 2.0 times 10 to the negative 3 moles of chlorine. And here's the equation. It says calculate the equilibrium concentrations of all the species and the value of K. So here is how we're going to do that. We're going to use a rice table, and I'm going to give myself a new screen because there's no way I can fit it on there. So we have our equation. We're going to start with that. That's the R of the rice table. So we have PCl5 is decomposing into PCl3 plus chlorine. So there's the R, I, C, E. So initially we have 8.1 8.7, and this has to be in moles, but it gave us moles, so that's good. So it's 8.3 moles. It said we had 0.298, right? Where did it go? I lost it. Oh, 0.298, sorry. And we don't know, we have no chlorine at this time, initially. So at the change, when this reaction happens, we're going to lose a certain amount, so we're going to say minus X, and whatever X decomposes, we're going to say plus X and plus X. Okay? If we had a coefficient in front of that, we would be like 2x or 3x, depending on the coefficient. Okay? So at equilibrium, okay, so we're going to add this up. So at equilibrium, that's what the E stands for. At equilibrium, we're going to have 0.0067 minus X.
Where did you get that number from?
I mean 8.7. Yes, I do.
How'd you know that?
It's just the non-cyclic notation.
Oh, no, that is 0.067 because we know what X is. I'm sorry. X is 2 times 10 to the negative 3 because it gave us at equilibrium, this was the concentration. So that's how much it changed. So we're gonna subtract it from there, so it's not X. So what I did to get that number, well, hold on, just wait. I'll write this different. So at equilibrium, we have 8.7 times 10 to the negative 3 minus 2 times 10 to the negative 3, which gives me 0.0067. Okay, this is going to be 0.298 plus 2 times 10 to the negative 3, which gives me 0.3 moles. So these are my equilibrium. Okay? In order to do the K, because we're going to be solving for K, we want the actual value, and so we're going to need Cl2 times PCl3 over PCl5. But it's concentration, correct?
Yeah.
These are not concentrations right now. What are these? Moles. We're lucky in the fact that what's our volume? 1 liter. So they become our concentrations. But if we had been in a 1.5 liter or 2 liter, we would need to divide by that because its concentration is got to be put into the K expression. So now we plug in 0.3, 2 times 10 to the negative 3, and we divide by 0.0067. Of course, those are all molar. So then we get 8.96 times 10 to the negative 2. So K is less than 1, so we're going to favor reactants. And the reason I have you write that now is if they asked you a follow-up question later on in a problem, you would have that in your mind that the reactants are favored because it's less than 1. It's not asking about that in that problem, but it's a good thing to tell yourself that. So if there's a follow-up question on an equilibrium problem, you have that in your mind. Okay? Now, sometimes they won't give you one of the equilibrium, but they'll give you the K value, and they want you to solve what the new concentrations are at equilibrium. So we're going to do another one like that. Okay? We're going to work quite a few problems. All right? Any questions on that? All right, then everybody got it written down? I'm fixing to erase it.
Yes.
Okay. Funny. All right, the next problem, I'm going to leave the blank paper up, but the next problem is exercise 10. And we've got carbon monoxide reacting with steam to produce carbon dioxide and hydrogen. And it tells you at that temperature that the equilibrium constant is 5.10. and then it says calculate the concentration of all the species if 1 mole of each one is in 1 liter flask. Okay? So we have to write our equation first. So we have CO plus H2O. Yep, this is the R. Yields CO2 plus H2. So that's the R. Do I need to do anything to balance that? Nope. So ICE. Initially, there's 1 mole of everything, it tells me. That looks like. All right. So as that reaction proceeds, the reactants are going to disappear by an unknown amount of X, and they are going to appear as plus X over here.
Wait, do you have a 2 in the decision?
No, it's just my pen is. I got a new stylus, and I'm getting used to it. That's a 1.
So they're all
Yeah, that's what the problem tells us. 1, 1, 1, 1. Okay. So at equilibrium, we have 1 minus X, 1 minus X, 1 plus X, and 1 plus X. They gave us that K is equal to 5.10. So that's going to be equal to products over reactants. So that would be 1 plus X times 1 plus X, which is squared, but I like to write it out first for people don't get confused, which becomes 1 plus X squared over 1 minus X squared. So then what can we do? Take the square root of everything, right? So square root it, all of that over there. So then we would get 2.26 is equal to 1 plus X over 1 minus X. So cross multiply, collect all your terms, blah, 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 do your algebra, and you should get that X is equal to 0.387.
Oh, yeah, no, never mind. I was kidding.
So now your concentration at equilibrium, CO, is going to be equal to your H2O concentration. So we would take one minus X, right, is how much? 387. So, and it's in molar, it's in 1 liter flask, so that makes things much better. And then, and you can, instead of writing them out individually, you are allowed to do it this way, whereas, because they're the same to each other, since we started with 1 mole of everything. So that's 1 plus X, so it's 1.387 molar. Okay? Any questions on that? No? Okay. Would you, where's the one that's got, oh, I know that 12 is going to need a quadratic equation. Okay? Well, 11 is going to be pretty straightforward, except that I need to show you something on 11 because we haven't done anything with a, actually, let's do 11 because we have a different, we don't have a 1 liter container, and we have coefficients. So we good before I erase? No? Okay. So on this problem, I did forget to mention this. If you have a K value, you actually, because these are reversible reactions, you need to calculate, if you can, a quick Q to see which direction are you going to do the equation in. But these were all 1s, so 1 squared over 1 squared is 1. So 1 is Well, how does it compare to K?
It's equal, so no shift.
1 is not equal to K. K was 5.
So less than 5.
Yeah, so we're going to be really studying the forward reaction. Because there are times that we could study the reverse reaction, and then the X changes. Okay? All right. So let's do exercise 11. So here we have hydrogen and fluorine gas reacting to form hydrogen fluoride gas. So we have H2 plus F2 yields 2HF. Okay? And they tell us that we have 3 moles of everything. 3 moles of each component, so 3, 3, and 3. It tells us that K is 115. So we need to calculate a Q real quick so we can see which way we want to do this reaction. So if we calculate Q, it ends up being
How do you calculate Q?
the same way you do K, but their initial concentrations. Yeah, so it would be 3 squared over 3 squared, which is 1. 1 is less than K, so we are going to be studying the forward reaction, the shift. Because sometimes you have to do that, because sometimes if you're doing the reverse reaction, then your X's are going to be opposite. They're going to be positive and minus. Yeah. So R, I, C, E. So we're going to do minus X, because we're going to be disappearing the reactant, and plus 2X over here. Why 2X? Because of that 2 right there. Okay? Because HF is going to appear twice as fast as the other ones disappear. Remember that from kinetics. Okay? So at equilibrium, we have 3 minus X, 3 minus X, and then 3 plus 2X. So our K value was 115. And we have 3 plus 2X squared. And then on the bottom we have 3 minus X, 3 minus X, which is also squared, right? Same thing as this. So we like it when we see that, because what can we do?
Cancel.
Square root it. So square root everything. All of that. So we get 10.7 is equal to 3 plus 2X over 3 minus X. So cross multiply, collect all your terms, blah, blah, blah. Do I need to do that, or can y'all handle that?
I'll do it with the calculator.
Well, here, I have it written down. So 32.1 minus 10.7x is equal to 3 plus 2x. 29 point. Okay, thank you. X is equal to 2.29. So your concentration of H2 is equal to your concentration of F2, which is equal to 3 minus 2.29 divided by 1.5 liters. Because we're no longer at 1 liter, so we got to make sure we divide by our volume. And so we get 0.472 molar. And then your concentration of HF is 3 plus 2 times 2.29 divided by 1.5. So it would be 5.056 molar. Okay? You cannot forget this step when you're not at 1 liter. When you're at 1 liter, you can just kind of, whatever it is, but you got to remember to do that. Okay? You also, if you're given the concentration for equilibrium at all 3, you have to be able to check and see which way is it going to shift. Okay? And
I'm confused when you do the Q thing in the beginning to determine which way the reaction.
to make sure I'm doing the forward reaction. It'll make sense in the next one because it's not going to be the forward reaction in the next one.
Yeah, but I'm saying, where did you get the numbers from? You did it.
You had 3 moles of everything.
Okay.
Yeah. And so you can quickly see that Q is going to be equal to 1. And so that is less than K. So you're going to shift to the right, meaning you're going to form the products. Okay? Because if we had favored the reactants, we would change our X values. They'd be plus on the other side. You'll see in the next problem. Let's just wait till the next problem. Okay? So we're going to do exercise 12 now. Erasing. Everybody good? In exercise 12, we have, now we're doing HI, so we're forming HI, and then it gives us our concentrations. And this time we're doing atmospheres. Okay, so make sure we're using parentheses here. So we have H2 plus I2 yields 2HI. Okay, so there's our R, I, C, E. So we have 0.01 from the problem, 0.005, and 0.5. Okay, so we got to calculate Q. So we have 0.5 squared over 0.01 and 0.005. That comes out to 5,000, which is much greater than K, so shift left. Which means as this reaction is going to reverse, and we're going to favor it this way. So we're going to be favoring the reverse reaction because that's the way the equilibrium is shifting. So that means we subtract. So over here, we would add X because this is what's going to be forming, and we would minus 2X. That's why it's important to calculate Q to see which direction is the reaction going to proceed, because this is all in a sealed vessel at certain pressures, and so which way is that equilibrium going to lie? Okay? So now we have 0.01 plus X we have 0.005 plus X, and then we have 0.5 minus 2X. It gave us the Kp value of 100, I believe. Yeah, there it is. So Kp is 100. So we're going to type in 100 is equal to 0.5 minus 2x squared.
But I thought that was our, I thought it was the other way now.
It's still, we're still doing products over reactants though, because that's what the equilibrium. Huh?
Is it still the product?
No, we're talking about equilibrium shift. So right now we're calculating what it was at the shift. When it's at equilibrium, that's different. At equilibrium, 100 favors the products, right? Because it's greater than 1. We're not at equilibrium because of the pressures and things that we have.
Okay, so you always go back to normal.
Mm-hmm. So that's plus x. And then we have 0.005 plus x. Well, no longer can we square root it, can we?
No.
We cannot. So this is where quadratic equation is going to come up. So multiply and collect your terms, and you should get 90 and 96x squared plus 3.5x minus 0.245 equals 0.
Where did you do that?
I mean, I just multiplied and collected and make it equal to 0.
Oh, okay. Yeah.
Okay? Now, if you have the quadratic equation in your calculator, it becomes very easy because you literally enter in your A value, your B value, and your C value, and it gives you your two roots. Okay? One of your roots will come back positive, one of your roots will come back negative. Sometimes they both come back positive. If a root comes back negative, you throw that one out. You can't have a negative root for X in this case, because that would be saying you have a negative change in concentration. You don't. You have to have a positive. So if you don't have that in your calculator, I do. So when I put quad form, I literally just enter in A, B, C. So it enter in 96, 3.5, negative 2.45. Okay? So my X becomes, and we can look at that when we're done with notes about trying to get that in your calculator. 0.035. No, that's just X. When you put it in as a quad form, it gives you the value of X. So then our hydrogen would be 0.01 plus 0.035, which is 0.045 atmosphere. Our I2, notice I'm using parentheses, not brackets, because we're dealing with pressure. Because we're dealing with pressure, so 0.004. Nope, because we're talking about pressure. We only do that for concentrations. Because the pressure is that's already accounted for, the pressure in that volume. And then HI is 0.5 minus 2 times 0.035, which is 0.43 atmosphere. So that is how you work that problem. Fun, huh? And then that brings us to Le Chatelier's principle. Any questions on why we did what there, why we did the reverse instead of the forward? Did you get why we did that? Okay. Now, if they didn't give you the products, you can't really calculate Q. So like if they have just said, because some of your problems they won't give you anything and your product will be 0 and you're calculating for that later. So if you can't do Q then you just assume the forward. But if they've given you information about the products and the reactants, you do need to calculate a Q to see which direction your equilibrium shift is happening for that particular data. Okay?
What is the lesson for HI?
Oh yeah, I'm learning to use this new pen. It's like I have to pick it up more than it is. I bought a knockoff Apple pen.
Is that 2 star?
It's 2 times 0.035 because that was minus 2x. That's like a what do you call it? Here, I'll do a time sign instead of the dot. Okay? All right. Moving to Le Chatelier's principle, which is much easier, and then that will be finishing off our notes. Okay? All right, I already went through those on the paper. That one. Okay, so Le Chatelier is a principle that states if a stress is applied to a system at equilibrium, the position of the equilibrium will shift in the direction that reduces the stress. And we did this in pre-AP, the very end of the year, so you probably don't remember it because y'all are ready to be done at the end of the year. The shifts occur to reestablish those equilibrium positions. So you need to think about, generally, when you're calculating the equilibrium expression, you're doing products over reactants. So you see how it affects that. Okay? So adding or removing a reagent causes the equilibrium to shift. Okay? So an example of here, as long as you keep milking the mommy cow will keep making milk. But if you stop milking the cow, he stops making the milk. Or she, not he. He's not making the milk. Okay? Increasing pressure causes the equilibrium to shift to the side containing fewest numbers of moles of gas. So you can't just say shift left, shift right on that one as a general rule. You have to look at which side of the equation has more moles of gas or less moles of gas, and it'll shift according to that. So you can't just say it's always going to shift to the left. It's always going to shift to the right. It depends on which side has what number of moles of gas. Okay? Adding a catalyst causes no shift. Okay? Remember in kinetics we talked about how it helps it lower the activation energy. Okay? but it does not affect the equilibrium position at all. It may mean you get to equilibrium quicker because you have a catalyst, but it does not affect the position, nor does an inhibitor. Okay? Changing the temperature, it reacts a lot like removing a product or reactant, but you have to know if you've got an endothermic or an exothermic reaction. Okay? So if I have an endothermic reaction, how do I treat heat? It's a reactant. If I have an endothermic reaction, heat is a reactant. So if I added or I heated the system up, which way would it shift? Away from what I added, so it would go to the right.
So if you put a cow in the oven, it'll shift to the right?
Only if it's a monomer.
Whatever. Okay? So here's this what we're talking about with exothermic and endothermic. Okay? So an endothermic reaction has a positive delta H, so we treat it as a reactant. So if we were to add energy to that system, it would shift away from where we're adding it, so it would shift to the right and make more products. If it's an exothermic, we've got a negative, so we treat heat as a product. So if I added heat, it's going to shift away from it, so it would actually shift backwards towards the reactants because you're shifting away. So you treat heat like a product or reactant, and so if you're adding it, it shifts away from it. Okay, so let's do some examples. Okay, here we have an equation of arsenic and carbon, and if we make these changes, what direction will they shift? So if I add carbon monoxide, it's going to shift left away from it. Okay, I'm just going to draw the arrows. You can right shift left if you want. Okay. The addition or removal of carbon or whatever, ASO4. So the addition is going to do what? If I add this stuff,
It's going to go right. If you add it, it'll go right. But if you remove it, it'll go left. Because then you'll have more moles.
nope, it's no shift.
Why?
Because they're solids. Solids do not appear in the equilibrium expression, so it would have no effect. Because they're solids. Yeah. What are the only things that appear in the equilibrium expression? Gases and aqueous. Gases and aqueous, not liquids, just gases and aqueous. So if you're dealing with solids, it doesn't have an effect on the equilibrium position. Okay. What if I remove the gaseous arsenic?
Right.
Yeah, it's going to shift toward where I removed it. Okay. All right, let's do, I think there's another one on there. Here we have this reaction, and how would those affect them? Okay.
No change.
We're talking about when the volume is reduced here.
It's a liquid, so does that matter? Because like there's a gas or solid.
Well, I mean, there is a gas, yeah. And when we change volume, when I reduce volume, what am I doing? Show the concentration.
No. The pressure goes up.
So it would shift right.
Why?
Because, by decreasing the volume, I'm essentially increasing the concentration of this. Because reduced volume means now I have more concentration of particles in a smaller space. Okay?
Okay.
Now, in the next one, that's all gases. So what would happen if so we have 1 mole over here, and we have, just kidding, 2. I looked at the wrong arrow. So I have 2 moles on this side, 1 mole on this side. So it shifts to the side with less. So right. When I increase, it shifts to the side with less moles. All of these are gases. I have 4 moles and 4 moles. So which way would it shift?
Nowhere.
Would not.
No shift because I have
How
equal.
do you draw an arrow for that?
You just say no shift.
Just point down.
No, you don't point anywhere. You just say no shift.
Point at the reader.
Goes up.
Okay, that is the end of the notes for this unit. Oh, there's another one. Sorry. It's not. Is it not in y'all's notes? Or did I just miss it? Oh, I just missed it. I'm sorry. All right. So this one we're talking about endothermic and exothermic, and we're dealing with heat. So in this first one, we have what kind of reaction? So endo. So heat is over here. So if I increase the temperature, which way would it shift?
Away from it.
Away from it, which would be to the right.
But that's not what it's asking.
It says for Victal, the value of K changes as the temperature
It'll increase because K.
increases, K increases.
Why?
Oh, because if you're making more products, your numerator now is larger, so that would be a bigger K, right? Because it's products over reactants.
Okay.
This is exothermic, right? So we're treating heat over here, right?
Sure.
So if we increase temperature, it's going to shift to the left, which means now I'm making more reactants. So what would K do? Decreases, because now my denominator is bigger, which would cause K to decrease. Okay? You need to be able to explain those. You can't just say, according to Le Chatelier's principle, you need to say it's going to shift away from the reactants, which would make more product, which would then increase your K value because your products have a higher concentration now, so it would increase your K. You've got to be able to explain that in as little words as possible. Okay? As little words as possible. And that puts us to the end.